Okay, I am Yasit Sandruan. So we are in the second video of the fan video series. In this video, we are going to learn about the impeller types or the fan types under centrifugal and axial fans. First, centrifugal. Under centrifugal, we can categorize them into major three types. First one, forward curve. Second, backward curve. Okay. Then radial. Under backward, actually, we can categorize them into another three types. First one, backward incline, then backward curved, and backward airfoil. If you like, you can put it into here as another one, airfoil. So backward means if I draw the impellers are bent towards the direction of the rotation. So this is the impellers, actually fan blades. So we call them impellers. They are bent towards the direction of the rotation, and opposite thing happen here. Backward curve fans, their impellers are bent to the opposite side. This is the rotational direction and they are bent to the opposite side. Incline, same, bent towards the opposite side. But the thing is, they do not have a curvature like this. Here they have a curvature, here they have a curvature, but there is no curvature here. Rotational direction is like this, and they are bent towards this side. And airfoil, if you can remember an airplane, okay, so it has a wing like this. Okay, if I cut this wing from here and see, okay, it is like this, something like this. Okay. So if I cut a small side from this wing, so those are the things in airfoil. So impeller is made up from this small slice. So those are the impellers of airfoil type fan. Okay. So that is airfoil. Something like this. Okay. So rotation to this direction and they are bent towards this direction. So that is airfoil, that is backward curve, that is incline, this is forward. Radial is something like this. It does not have any curvature and they are not inclined to forward or backward. So they are called radial. So by looking at this shape of the fan impellers, we can tell a lot of things. Let's see how we can do that. Okay. So due to the shape of the impeller, the characteristics of fans vary. Let's see how we can analyze those things. Okay. For that, we have to draw the velocity diagram of these impellers. First, we will look forward curve fan. Rotation is for this direction and this is the impeller. So if this impeller is rotating in this direction, okay, in this direction, always due to this sorry, this is backward curve. This is forward curve. So always this impeller try to hit the air in this direction. Okay, when they are rotating, this impeller try to hit the air in this direction. Because of that, at this location, air has a velocity to this direction. Okay, let's say it is V2. V2 is the tangential velocity in this direction. It is due to this impeller is trying to move air like this. And also, you know, when there is something in rotation, they have centrifugal force. Because of that centrifugal force and this curvature, air is trying to move like this. Okay, so air has a velocity, another velocity in this direction. Okay, due to this curvature and the centrifugal force, it is trying to leave the blade impellers in this direction. So let's call it V1. It is the radial velocity. Okay, so we have two velocities for the air particle. For air particle, let's take the resultant velocity. For that, I can draw this figure, and from this line I can take the resultant velocity. Okay, this is the resultant velocity. So it is very clear, always in the forward curve fan, VR is greater than V2. Here VR is always greater than V2. V2 means the velocity exerted on air particles due to this rotation. That means V2 is equal to the what? V2 is the rotational speed. That means fan speed. VR means it is the velocity ultimately the air particle obtain. Okay, so in this figure, by analyzing this figure, we can conclude that air particles have more velocity, a greater velocity than the rotational speed. Okay, then backward curve fan. Rotation for this direction and impeller something like this. So radial velocity for the forward curve fan is like this, and but here rotational velocity for this direction due to this curvature and centrifugal force. V1, it is the radial velocity. This impeller rotating in this direction. Because of that, they try to move this air in this direction. So it is the tangential velocity. So in order to get the resultant force, this is the resultant force. Sorry, resultant velocity. So it is very clear, always VR less than V2 here. That means air particles leaving this backward impellers have less velocity than the rotational speed or the fan speed. Then the radial rotation like this, and radial velocity is like this, V1. Tangential velocity like this. If you take the resultant, it's like this. VR. So this is backward curve, this is radial. Okay, let's analyze the characteristics. So it is very clear that the air particles releasing or moving the impellers of forward curve fans has a greater velocity than the fan speed. Because of that, this fan does not need to rotate in higher RPMs. RPM, that fan speed. So this forward curve fans does not need to rotate in higher RPM. So speed is less compared to backward curve fan. In backward curve fan, always air particles leaving this impeller has a less velocity than the fan speed. Because of that, to get same air flow, if we can compare this fan and this fan, if we want to get same air flow, this fan have to rotate in higher RPM, in higher speed, because air particle moving, releasing or removing or leaving this impeller has a less velocity than the rotational speed. So because of that, we have to speed up this backward fan in order to get the same air velocity compared to the forward curve fans. So speed is, we have to speed up it. So speed is higher now. We have to speed up the fan. So this speed means not the velocity of the air particles. This means fan speed, RPM. Already this air particle have a greater velocity than the fan speed. Because of that, we don't need to speed up the fan. That is why they work in lower speed. Okay. Then second one, pressure. Here, okay. Before that, what about the airflow? Okay, airflow. Second, airflow. This fan have a greater air velocity. That means greater airflow. Airflow means per 1 minute how much air volume will be handled. So as the velocity is higher, higher volume will be handled. That means airflow is greater compared to the backward curve fan. Airflow is low here. Okay. Then we can decide the pressure. Okay. What about the pressure? Here, pressure means static pressure. So you know there are two types of pressure we are dealing with. One with the velocity. Okay. If this air particles are moving in this direction, they have a velocity. Because of that velocity, we have a pressure called what? Dynamic pressure. In here we also refer that as velocity. But if we consider the sample of air inside something, inside a box or something, the pressure exerted on this wall can be identified as what? Static pressure. Static pressure. So, if we consider a duct and air is moving in this duct, okay, like this, in this air, okay, if we consider this air, it has both dynamic and static pressure, because this wall, the air particle exerted some force, that is static pressure, and also this air particles have velocity towards this direction. Because of that, they have dynamic pressure also. In order to have some static pressure, velocity does not need to be zero. Okay, it does not need to be zero. If this air have velocity, they also have a static pressure. But the thing is, energy of this air sample or air stream, energy of this air stream does not change. And also, components of energy are dynamic pressure and the static pressure. Okay, component of the energy of this air stream are dynamic pressure and static pressure. What happens if the velocity of this stream increased? That means dynamic pressure should be increased, because dynamic pressure means velocity, due to velocity. So dynamic pressure will be increased if the velocity of this stream is increased, but energy should be constant. To be constant, this static pressure should decrease. Okay, if static pressure is increased, dynamic pressure should be decreased. So dynamic and static pressure has a relationship like this. Okay, so if we consider the forward curve fan, air velocity is higher compared to backward curve. So air velocity higher means dynamic pressure is higher, static pressure is decreased. So actually pressure means here static pressure, now static pressure is decreased. When we compare to the backward curve fan, their velocity is not much higher. That means dynamic pressure is not very much higher. Because of that, static pressure is higher. I will come to that point when we analyzing the fan blade length. Also we come to this point. Then fourth one, as this fans does not rotate in higher speed, they don't want this fan to be very heavy. Okay, because of that it is lightweighted. Okay, this is very lightweighted. But this backward fan should be able to work in higher speeds. Okay, that means their fan should be, they have to be constructed a bit heavier than the forward curve fan. Because of that, cost of this forward curve fan is less compared to cost of the backward curve fan. Backward curve fan manufacturing cost will be higher than the forward curve fan. Okay, because they should be able to work in higher speeds. So it is not the case in forward curve fans. Okay, another one. What about the noise? As this fan does not work in higher speed, the noise generation is less. Okay, and also dust accumulation. Okay, due to this curvature, let's say this is forward curve fan rotating in this direction. Okay, if this fan impeller rotates in this direction, air hit on this impeller like this. But if we compare it to a backward curve fan, this impeller rotating in this direction, air hit like this. But this air can leave like this. But it is not the case. Air can leave like this. But here it is not the case. It's directly hitting in this way. So if we compare these two impellers, always the force on this impeller type due to this curvature, and if we compare this one to this, always the pressure or the force on this impeller by the air particles is higher than this curvature type. Okay, it's very clearly seen. Okay, so because of that, if we increase the blade length, force is greater. Okay, force is greater because this forward curve impellers has a scoop effect. Because of that, they can handle more air. So that is why airflow is higher. We can argue from that point also. However, if we increase the blade length like this, the pressure on this impeller wall is way greater. If we speed up to a certain level, this impeller can bend like this due to this great force exerted by the air particles. Because of that, forward curve blade length is less, not very much. Okay, blade length is less compared to backward curve fan. Backward curve fan does not have some problem or issue like this. Because of that, they can increase the blade length. Okay, so if the impeller is bent like this, our structural integrity cannot be achieved. That means our indent purpose can be achieved if this impeller is bent like this. Because of that, we don't increase the forward curve fan blade length. 8 blade length is less compared to backward curve fan. Here it is higher. Okay, we skip that dust accumulation. So forward curve and backward curve fan both has a curvature like this, but a radial fan does not have a curvature like this. Because of this curvature, both forward and backward curve fans has a dust accumulation effect on these impellers. So if we consider dust accumulation, which one is the good one? The radial one. So in radial blade, dust accumulation is less compared to these types. Okay. Then other thing is, if I consider forward curve blades, they have a less length. Okay, because of that, in order to handle more air, they have to increase the number of impellers like this. Okay, number of impellers like this. But backward curve fan has a greater length compared to forward curve fan. If I draw in same diagram, may look like this. They have greater length, because of that they don't need much impellers as forward curve fan. Okay, so if you compare the cross-sectional area between two impellers, so this, if you consider backward curve fans, this cross-sectional area is increasing here, is increasing because their length is higher and also less number of impellers are there. Because of that, their cross-sectional area is increasing. But that effect is not much higher in forward curve fan. Here their cross-sectional area is not increasing very much because they have a less length. Okay, so because of that, cross-sectional area between two impellers is increasing in backward curve fan more than the forward curve fan. What happens is, if the cross-sectional area is increasing, we know that velocity is decreasing, because in order to move same flow rate, okay, if the cross-sectional area is decreasing, we have to speed up in order to move the same flow rate. But here it is increasing, because of that velocity should be decreased. We know that if the velocity is decreasing, that means dynamic pressure is decreasing. That means static pressure is increasing. So that is why pressure in backward curve fan has increased. Okay, so because of this effect, that means if we compare the forward curve fan, their cross-sectional area is not increasing very much compared to the backward curve fan. Because of that, they cannot build up static pressure. They cannot build up static pressure because cross-sectional area is not increasing very much compared to backward curve fan. That means velocity is not decreasing compared to backward, and that means static pressure is not increasing compared to backward. Okay, that is why pressure here, this pressure means static pressure is now decreased. So because of that, in forward curve fans, let's say this is the forward curve fan, this is the impellers. Forward curve fan, we have to make a spiral casing like this, okay, or the scrolling casing like this. Backward curve fan also have this housings or scroll housings, but backward curve fan has an ability to work with even without this housing unit, because they have good static pressure. But forward curve fan does not create static pressure very much. Because of that, in order to make convert velocity pressure into the static pressure, we have to make something like this, a housing. Why? When we collect something inside a container, something like this, what happens? Static pressure is high. We compare airflow which move freely, and if we try to collect this airflow inside something, that means if we collect something inside container, static pressure will go high. That's what's happened in this case. Before giving out the air, they try to collect it inside a casing, it's called casing, and then deliver. Because of that collecting process like this, static pressure, the energy will be converted from the velocity pressure into the static pressure. We know for the energy, what are the components? Dynamic pressure and the what? Static pressure. Here dynamic pressure is more. But because of that, we make a scroll housing like this. Because of that, dynamic pressure will be decreased and static pressure will be increased. So that is how we convert the velocity pressure into dynamic pressure in forward curve fan by using a scroll housing. But the thing is, not all the dynamic pressure is converted into static pressure, okay? So, when it comes to this forward curve fan, scroll housing or the housing is a must. But when it comes to the backward curve fan, it is not a must. We can perform, or backward curve fan can perform even without the scrolling housing. Okay, as an example, plug fan. It does not have a housing unit. Okay, so that is why backward curve fan need a housing, and this can work with even without a housing. Okay, so if you can remember all those characteristics we obtain from this velocity diagram and the shape, and also this velocity diagram is obtained from this shape. So by looking at the shapes of the impeller, we analyze lot of characteristics. Okay, each of these characteristic we know now. We know the reason behind those features. Okay, how this feature came. Okay, by analyzing the shape of the impellers. Okay, so that's for the characteristics, and now we can go to the efficiency of these impeller types. Okay. So actually, what is efficiency? It is how much output is there compared to input. Okay, in fan efficiency, there are two types of efficiencies are there. Okay, first one, static efficiency. Okay, so what is the output of the fan and what is the input of the fan? Actually, output is always the pressure development and the air flow. How much is the pressure? That means total pressure, and how much is the air flow. But in static efficiency, we take only static pressure rise. So, however, pressure and airflow. Pressure and airflow is the output. But in static efficiency, we take only static pressure and airflow. This is cubic feet per minute. How much of air volume in cubic feet are delivered within a minute. So, however, the output is pressure and airflow. Then input power. How much input power we give to this fan. Then other type is fan total efficiency. For the total efficiency, we take not only static pressure rise, we take total pressure rise and airflow, then input power. Okay. So in this total efficiency, what is total pressure? You know that first one is what? Dynamic pressure, second one is static pressure. Okay. Actually, we learn radial, backward incline, backward curved, backward airfoil, and forward curve fans. If we compare the efficiencies of these impellers, okay, we have a greater efficiency for the forward curve fan than the radial fan. This is forward curve fans. Backward incline fan efficiency is greater than the forward curve. Backward incline. And backward curved fan efficiency is greater than backward incline. And great efficiency we can obtain from actually airfoil. Okay. So this is how efficiency works. We have a great efficiency in backward airfoil. It is about 85 to 90. Efficiency is there. If we give 100% energy, we can take, or as an output we can take 90% of the energy we input. Okay, so someone can have a doubt of this pattern because when we are doing the velocity diagrams, I told you to take constant airflow, if I consider forward curve and backward curve, to get same airflow, this fan should rotate in less speed than this fan. In other words, if I consider same rotational speed, airflow is less than the forward curve fan. It's same thing. At the beginning, I compared with a constant airflow. That means if I want a same airflow, I need to speed this backward curve fan more than the forward curve fan. The rotational speed is higher compared to this one. Someone can say if the rotational speed is higher, that means more input power we should give to the fan. That means, but if still backward curve fan is, its efficiency is higher than the forward curve fan. What is the reason for this? Okay. Oh, this scenario can be analyzed as this also. If we compare constant RPM, that means same fan speed, this backward curve fans produce less airflow compared to the forward curve fan. Same thing. Okay. So if I take this formula for the efficiency, okay, you can clearly see if the airflow is less, that means if the airflow is less, efficiency is less. Okay, if the airflow is less, efficiency is less. So in the backward curve fan, airflow is less. Forward curve fan airflow is increased or greater compared to the backward curve fan if you compare them in a constant RPM. But still backward curve fan's efficiency is greater than the forward curve fan. So actually what is the reason for this? Okay, before moving on, let's consider this example. So if you want to lift something, so this is the weight and you are going to lift it with your hand. Okay. So in this scenario, if you want to speed up this process, that lifting process, you can slowly lift it. If you want to speed up this process, that means you have to give more energy, you have to put more work on this process if you want to speed up. That means energy is high. If you compare it to the fan, that means if the rotational speed or the fan speed is increased, that means you have to give more energy. But the thing is, for this thing, energy does not depend only on the speed. Okay. So what about if I increase this weight? If I increase this weight, what happens? In same speed, okay, in same speed, now weight is increased. So I have to give more energy to lift this one. Okay. That means for the speed, for the energy, or for the power, not only the speed but also this weight is a factor. When it comes to the fan, that weight, that factor is equal to something like this, something the air flow, how much of air volume, how much of air mass will be handled by the fan. If this volume of air or the mass of air is increased in same speed, in that scenario also we have to give more energy. So it is true, this air flow is increased in forward curve fan. That means this fan efficiency should be increased, but if the air flow is increased, that means more volume of air will be handled. That means more air volume will be handled means we have to give more energy to the fan. That means this input power is also increasing. But the thing is, this increase is more than this increase. That means if this is increased, fan efficiency will be increased, but input power will be increased in higher amount. That means if it is increased, this will be decreased in higher amount. Okay. So actually, due to this, fan efficiency should be increased, but due to this, fan efficiency is decreasing in higher amount than this increase. Okay. So because of that, backward curve fan has a great efficiency than the forward curve fan. And also backward curve, backward incline and airfoil fans has another characteristic. We call that non-overloading characteristic. So actually this is airflow and this is BHP, that means brake horsepower, the power we should give to the motor in order to rotate our fan blades. So if I draw the brake horsepower curve for the backward fans, it may look like this. It is increased to a certain point and then it will be constant or decreased. But for the forward curve fan, it may look like this. It is increasing. And for the radial, it may look like this. Increase in this fan is greater than this radial. This radial, this is forward curve, and you can see this. Okay? And this is backward curve. So that is how power behave. That means if I increased my airflow to a certain amount, this backward curve fan does not overload the motor. But there is a possibility in forward curve fan to overload the motor. Why? Because their power is increasing. When airflow is greater, their power is also greater in great extent. But here, if you compare the backward curve fan, their power is constant or decreasing a little much. Okay. So, if I choose a fan for the backward curve fan, if I choose a motor for the backward curve fan, who can facilitate this point? Who can achieve this point? Okay. This backward curve motor does not overload at any time, because whatever the airflow is, it does not overload. But we cannot find something like this in the forward curve fan. If the airflow is increasing, it's keep on increasing like this. Because of that, power is increasing. That means motor can be overloaded. Okay. So that is another good characteristic in backward fans. We call that non-overloading characteristic of backward curve fans. And backward airfoil fans also have this. So this is overloading. So forward curve fan has an overloading characteristic. And we call that non-overloading characteristic also as self-limiting characteristic. Okay, self-limiting characteristic. Okay, then we can draw the efficiency curve. Actually, this is not regarding fan curves. We have a separate video for the fan curves, but as I started talking about efficiency, I will draw the efficiency curve for a centrifugal fan. It is something like this. If I draw the static efficiency curve, it may look like this. Why? This is airflow actually. Okay. So if we consider the static efficiency, what are the factors or the variables that calculate the static efficiencies? Static pressure is CFM, that flow rate, that input power. So at the beginning, flow rate is 0. This is airflow, that means flow rate is 0 here. That means at the beginning it is 0. That means static efficiency is 0. Okay. And at the maximum airflow, static pressure is 0. At the maximum airflow, static pressure is 0. Why? We are going to learn that in fan curves. When we are doing fan curves, we are going to learn that thing. But for the time being, so let's consider at the maximum airflow, theoretically, static pressure is 0. Because of that, fan efficiency is 0. But if we consider total efficiency, for the total efficiency, this figure has two things. That means total pressure has two components: dynamic pressure, static pressure. So if I draw the fan efficiency for the total efficiency at the beginning, that means in this point airflow is 0. That means for the total efficiency also, this curve may look, this start from this point and it goes like this. Okay. So at the maximum airflow, in that point, we learn that static pressure is 0. This is actually what? 0. But total pressure does not totally depend on static pressure because it has another component, that means dynamic pressure. So at this maximum airflow, dynamic pressure is not 0. Because of that, there is an amount for the total pressure. Because of that, at the maximum airflow, total pressure does not come to this axis. So this is total efficiency. This is static efficiency. This is static efficiency. If I consider total efficiency, this point will be my what? Best efficiency point. Okay. This is a good feature when we are learning about fan selection. So we are going to use this best efficiency point with some other fan curves to select some fans. Okay, but I am not going to tell those features in this lesson because we haven't learned about fan curves yet. After we learn fan curves and with this fan efficiency curves and this best efficiency point, we are going to make decisions about fan selections. Okay, so for the centrifugal fan impellers, that will be the end. But now we are going to look about the axial fans. Okay.
Okay, when it comes to the axial fans, we can categorize those into major three types: tube axial, vane axial, and propellers. So this is the tube axial fan. You can clearly see it is inside a cylinder shaped housing. So for tube axial fans, we need a housing. So this is vane axial fan. Previous one was tube axial. This is vane axial. For vane axial, we have impellers. After the impellers, you can clearly say there are guide vanes. Because of that guide vanes, we can make uniform the airflow. Okay, we can make it uniform, and also because of that, we can increase the efficiency. So this is propeller, type of a propeller, and also this is a type of a propeller which can be used in airplanes. When it comes to the efficiency, propeller has the lowest efficiency. It is less than 50%, and also when it comes to the tube axial, it is around 65, and also in vane axial fan, it has the highest efficiency in this category. It has around 38 to 85 percentage efficiency is there. So those are the types of axial fans.
Okay, so this is the summary of today's video. So this is centrifugal fans, this is axial fans. Okay, so under radial blades, what are the features? Pressure is higher. CFM means the airflow is somewhat medium, and efficiency of the radial blade is somewhat equal to tube axial fan. Actually, in this category, it is the lowest. It has the lowest efficiency, and durability is higher because dust accumulation is less in radial blades. Actually, it is one of the reasons that is durability is high. And also when we compare the power, so that is how power changes with the airflow. Okay, so what are the applications? Dust extraction applications. So material handling applications are most suitable because dust accumulation is less, and higher pressure applications are also good for radial. Forward can move large airflow against lower pressure. That means they develop lower static pressure but moves large airflow. Efficiency is greater than the radial, but relatively it is low. Generally it has very low efficiency, and the power is gradually increasing with the airflow. Because of that driver, that means the motor must be carefully selected, because we have to consider the airflow. If the airflow slightly changed or slightly increased, that power is increased in huge amount. That means that motor can be overloaded. Because of that, motor must be carefully selected. Backward curve fan, pressure is high, CMF is high. We learned that if we consider forward curve and backward curve fan generally produce lower CMF, that means lower pressure. But why it is higher? That means How about the power curve? This is the power curve. So if we have a higher airflow application, and let's consider it does not have a certain airflow. Airflow can be changed, and also airflow is higher and also it is not a constant figure. That means airflow can be changed. Airflow can be changed. This is the airflow. But if I consider the forward curve fan, if this airflow slightly changed, what happens? Motor can be overloaded, because if this airflow is slightly increased, power for the motor will be hugely increased. So for a higher CMF, and if we have an uncertain airflow, backward curve fans are good. That is why I told you it is suitable for higher CMF, and also if we have an uncertain airflow, backward curve fans are good. And that is how power curve of the backward curve fans, and efficiency is higher. Somewhat generally it is higher. Airfoil pressure is higher, like backward curve fan, backward airfoil. Efficiency is higher. It is the most highest efficiency in this category. Airfoil fans, airflow is higher. It is suitable for the large airflow applications, and that is how pressure acts with the airflow. Okay, so when it comes to the application, forward curve fans can be used for the residential HVAC systems, unit packages, and most important one is it should be clean air. Okay, for the clean air supply or extraction application, we can use forward curve fan. And not only forward curve, backward and airfoil, we want clean air supply and clean air condition. Okay, otherwise that dust accumulation can be a huge problem for this forward and backward types. When it comes to the axial fan, propeller, low pressure, low airfoil, low velocity, low efficiency. What are the application? Air circulation. Air circulation means, let's consider your room. You have a table fan and air is circulated through this fan. So those applications, ventilation, exhaust systems, we can use propeller. Tube axial, pressure is somewhat medium, airflow is higher, energy is higher than the propeller. Efficiency higher than the propeller, and power curve has a dip like this and gradually decreased. So HVAC systems, drying ovens, exhaust systems, we can use tube axial and vane axial fans. Pressure is higher, airflow is somewhat medium, and you have seen that there are guide vanes which makes the airflow uniform, and also it makes the efficiency, it increases the efficiency. If we consider these three types, highest efficiency we have in vane axial fans. Okay, so they are useful for higher pressure applications. Okay, so actually this is the summary, and also in this lesson we have learned about impeller types and how that shapes, due to that shape, how we can decide some characteristics of these fans, and we also learn about the efficiency of the impellers. Okay, in next video we are going to talk about fan curves. Okay.